Imagine you were hired by the Mall of America. The first task they gave you was to find the entire square footage of every nook and cranny that the mall has. How would you go about doing that? You would probably use the basic concepts from our Chapter 5 unit: right triangle trigonometry, law of sines, law of cosines, and the new area formula. These concepts would be vital in finding a total square area of an object or a shape. That's what your Chapter 5 project is going to be about. Ultimately, you're going to be picking your own shape or building or area to analyze using technology. But before we do that, we need to talk about some basics of different shapes and polygons and how would you go about finding areas. So our first warm-up is this. It says draw line segments so that the polynomial is divided into triangles. And do you think this is possible for any polynomial? Remember, a polynomial is just an enclosed shape with sizes up to 3, 4, 5 on to infinity. If we look at this one right here, this is a pentagon. To draw line segments that divide it into only triangles, and I want this triangles that don't overlap, how might you go about doing that? Well, you could start by going from this one vertex to the other, from here to here, and in doing that, we just created 1, 2, 3 different triangles. Now, if we go over here and look at this 7-sided object, which is called a heptagon, we can do the same thing. I'm going to start by connecting these two vertices, and then these two, the next set, and the next set. In doing that, we've just created for ourselves 5 different triangles in here. So we can clearly see that any polygon can be made into only triangles. This is beneficial for your project because we could use right triangle trig, law of sines, and law of cosines to help us find any missing angles or side lengths. Then we can use our area formula and compute the complete area of these objects. Let's look at some other examples. On this one, they want us to try dividing the following polygons into triangles again. So to do that, one thing you could possibly do for this object is you could go from here to here. You could drop down here to get a triangle. You could also go here, and maybe you wanted to do that. So in doing so, we've just created for ourselves, again, 5 different triangles, and that could be helpful in preparing for our project. If we look over here at this arrow, this one can be done in about 3 different triangles. We could drop right here, and we could also go here, and we'd have 3 different triangles, and we could use our triangle formulas to find the areas. So as a formal introduction to your project, this basically says you've learned how to find the area of shapes throughout your life. You've used grid paper, you've used formulas for rectangles, for circles, for squares, for triangles. In the later years in math and calculus, they'll learn how to integrate. But the one thing we know we can do is this. You can build any polygon out of triangles. So that means it covers many different shapes: trapezoids, parallelograms, hexagons, heptagons, octagons, and so forth. So the goal of this project is you first need to find a plot of land, a house or a building, part of a building, an object on Google Maps, something that interests you. It could be where you live, where you work, etc. And then we're going to use Google Maps to find that particular location. Our goal then is to find the total area of that piece of land and convince a person who's interested in this land that you accurately measured it and computed its area. You're going to use your math smarts to prove to them that you are correct. The requirements for this project are as follows. You can use area formulas for other polygons and circles. However, the following requirements will be assessed within the project. The first point is the law of sines and law of cosines must be uniquely used at a minimum of 5 times. The second thing is the triangle area formula, either the sine formula for area of a triangle or the right triangle area formula must be used at a minimum of 5 times. Point 3, you must have a complex enough shape. That is, it's not adequate to find the area of a rectangular plot. This is a higher level math class. We're more advanced than that. Mrs. Landon must approve your shape before you begin the formal work on your mathematics, so get that checked off. And then the last thing is step 4. You can write, type, or make a presentation that reports how you measured the area, how you calculated the area, and your overall ability to convince a person interested in the land that you are correct. The detailed diagrams are required. This is a geometry-based project, so we need to see pictures. Remember, a picture is worth 1,000 words. Think about who your audience is. Are you trying to sell a potential buyer on something? Is someone doing a census or a survey? Are you hiring a contractor to do something to your house and they need some measurements? Are you meeting with the IRS and they need the exact data? Now, some of the tools that you can use, I'm going to show you how to use Google Maps and Wolfram Alpha. You may want to use GeoGebra. You could actually go on site, use protractors, rulers, or a tape measure. That's probably not the most reasonable thing, so then you're going to have to use some type of technology. The grading is going to be used in the rubric. Basically, the 4 requirements here have to be met, and so let's take a quick look at the rubric. So you can turn in, like I said earlier, the project in any reasonable format. I'm very open to that. Electronic, paper-based, however you would like to do it. Just make sure to get your design approved by me before you do the math. The 5 categories used in the scoring rubric, the first is going to be the formula requirements. Remember on the previous page talks about meeting various law of sines, law of cosines, and area formulas. So if you meet all requirements of the minimum number of formulas used are met, you can get a 4. And it would vary from there from many to some to few or no. Then if we continue on, the next is the accuracy of measurements. Are all the reasonable and appropriate measurements used in your actual figure, or is it many, some, or few? Third category, the explanation of the procedure used. Here, completely your clear and logical explanation on how the total area was computed. Can I look at your presentation or what you hand in and tell exactly what you did on what various components of your drawing? Or is it somewhat clear, not very clear, or not at all clear or logical in that case? Also, the mathematics used as the 4th category. Are all accurate and appropriate formulas? Many accurate and appropriate formulas. Are you using the right formulas in the right places? And again, showing the work in your explanation. And then the last one is convincing of argument. Are you completely convincing that everything is correct? How are you going to sell me on the fact that your area is appropriate? So just don't show the math calculations in the formulas. Sell me that you are actually correct on that. And then this project will be out of a total of 5 points in the gradebook. So you might ask yourself, what are some appropriate objects or shapes or buildings to look at? I particularly like the Mercedes-Benz, so I looked at the Bloomington dealership, Feldman Imports Mercedes-Benz. This building, to me, when I first looked at it, the bottom half here is definitely a quadrilateral or a rectangle. Very easy to find the area. But I noticed here in the various showroom windows, they're going to have some various angles where I could compute and come up with some triangles. So I would say picking this Mercedes dealership for your project would actually be an adequate shape with enough complexity. These side windows on the showroom are going to be quite a bit of work, but it is very reasonable. Another potential thing, maybe you want to look at the area of South Dakota. If you want to show me how to measure that. You're going to notice, obviously, this side of the state is very rectangular and very basic. However, when you get over in this area and in this area here, it's going to be much more complex to do, so you will hit some trickier spots. That would be a reasonable project. What about finding the area within target field? Maybe you're going to look at just the inner field here. Maybe you'd look at the building. Would that be adequate for a project? At initial glance, I would say probably. This corner here looks like it might be a little more detailed in terms of having an angle, something more like a triangle corner. So that could be difficult. That would be something we want to investigate a little bit more if there's enough complexity in it. Because you need to pick objects that have a little bit of complexity. If they're too simple, they're not going to count. What about Hilltop Primary School? I went on Google Maps and here is the image of that. I will tell you, in my opinion, this is actually a very complex project with lots of angles and corners. And this might be too complex to actually deal with. The reason is this location here is a major polygon where you could sector it off into a variety of different triangles or different types of polygons, which could be quite complicated. This area here obviously is not difficult with a rectangle, but these other portions might make it too hard to do. Another school, I looked at Dassel Middle School, and their high school is connected. This one, unlike Hilltop, is much more linear in terms of their line structure, but I really like this corner here, you kind of see that triangular portion. You also see a little bit of details and complexity in there. This is a pretty big building, but it's something you could look at. What about Lord Fletcher's on Lake Minnetonka? When you first look at the overview of this, it is very linear and rectangular and would be easy to do in terms of rectangles. Now I have to caution you, picking a shape like this may not be complex enough unless you add some complexity to it. I could easily partition this off into just rectangles and probably get this project done in 15 minutes, and that's not the intention. The one requirement here is you do need to be using the rectangular shapes. So if you were to do something like this, you'd really have to partition it off into some more complex triangles. So you're using law of sines and law of cosines. I would venture to kind of stay away from something that is too simple in nature like this, which is made up of all rectangles, because you're going to have to make it more complex. What about the Xcel Energy Center in St. Paul? I think the Xcel Energy Center actually has some really nice details. This right here, the doorway entrance would be involved. You could kind of ignore all the seats and just look at the outside framework of the entire Xcel Energy Center. So that would be an interesting one to try. If you're into the arts, how about the Walker Art Center? I tried looking at this one and I thought, it was very streamlined and somewhat simple, but I liked, for example, this corner wasn't too bad. It might be a little too simple still. I'd have to think a little bit more about the Walker Art Center. Because it is almost just very linear and not a lot of complexity in the building itself. What about the Highland Ski Area building over in Bloomington? This building right here could be complex enough. On the front end right here, very rectangular and not hard to do at all. However, as you get into this location right in this spot, you may be able to find enough triangular work happening. Also, possibly right in here, you're going to encounter some triangles. So this could be a good project. Caribou Coffee here in Mound. This is the outline of the Caribou building. Again, this might look a little simple at first, but I could possibly see maybe having enough angle information in here or here to get some triangles. You really want to be thoughtful, though. This may not be complex enough unless you add some more complexity to it. Now, once you find your object, you want to start getting the measurements of all the sides and figuring out which shapes you're going to create, such as squares, rectangles, and triangles. I'm going to go back to the Mercedes dealership in Bloomington and show you how I'm going to approach this corner display window and get a measurement. You can do this all within Google Maps. So in step 1, when you're in Google Maps, just right-click, and when you do that, you want to select down here, it says Measure Distance. After you do that, it's going to change so that you click and drag the segment as you need to get your first measurement. So you're going to notice after I did the measure the distance, I clicked on the screen and I got this segment, so I dragged it to get this measurement. What I'm trying to do is actually create a triangle for this region here. So when you do that, notice right here it actually shows the distance is 48.87. So I'd want to record the length of that in feet. And that's what step 2 talks about. Now, step 3 says to get a second segment and drag it where needed. So just click one more time. When you click again, another segment's going to get created. I needed to get this little part of the window frame, so I just dragged it from there. Now, you have to be careful because at this point, when you look at the screen, what it's going to show you is the distance right here says that the distance is 58.47. That's the total distance of both of these segments. So to figure out the distance of this little segment, I'm going to take this total distance of the 58.47 and subtract the first distance of our longer segment of 48.87. And when you do that, you're going to get that the distance of this little line segment here, I have stated, is 9.6 feet. So then I would label that measurement also. Now, step 4, get a third line segment, and we're going to try to connect from here to here. So in my step 4, you're going to see the next picture. I did create the third line segment from here to here. Now if you look at the screen at the total distance, what it's going to state is it's going to have the total distance down here, and it's going to say it's 105.85 feet. So to figure out the length of this third segment, just take the 105, subtract out the total of the two segments, and you're going to get 47.38 feet, which means this third segment is that length. Now, after you have all three measurements, you are going to notice in step 5, it talks about here, it actually tells me the total area. So I know the area of this triangular region is 227.06 feet squared. Now, you'd think the project's done the work for you, but it hasn't. You need to show me the mathematics behind that. You cannot assume this is a right angle anywhere. You must find one of the angles. The only way to find one of the angles is to actually do law of cosines to find the angle. And then you would go do the 1/2 AB sine of C formula. So let me show you, and I'm going to set up the law of cosines for this triangle here. So notice the formula I chose to write is this one here. I'm going to take this side length here and find its matching angle. So the angle here and this side length here match up. So remember to write law of cosines. I'm going to start with this side length here and square it. I'm going to add to it the other two side lengths squared minus 2 times each of those side lengths. And then I'm trying to find what I'm calling angle A. And angle A is my red one. Once I do the math, I'm going to ultimately get the measurement of angle A. And I'm going to get what the value is for that. So this is going to be in degrees. Then the last step is I need to actually figure out how did they get the area of 227 feet squared for this. All you have to do is you can go in, remember, and use our formula. The side angle side formula is 1/2 AB sine of C. Now for me, I'm choosing my two side lengths as this side length, and this angle. So you always choose the angle related to the two side lengths you have. So for this formula, all I have to do is I'm going to come in here and I'm going to keep it as 1/2. Again, the two side lengths I'm using are this and this, so I'm going to write it as 48.87 and then 9.6. Now don't forget the word sine, that makes it very important. And the angle I have to use right here is because I chose these two side lengths, I use the angle created by that. So for me, whatever I found this angle measurement was, goes in here. So in my calculator, when I go ahead and I compute 1/2 times this number, and the sine of the angle, it should be incredibly close to, if not the exact same number that Google Maps computes. Now this is the work you have to show within your project. And don't forget, you have to show law of sines and law of cosines a minimum of 5 times to get your angle measurements. In addition, you have to show the side angle side area formula 5 times for at least 5 triangles. Show the work in between here to how you got the angle. Just don't jump from the formula to the angle measurement. Do the actual mathematics, because that's what I'll be grading. As some helpful hints, when you're looking at the rubric that's actually in the project, so here's the rubric down here on how you're going to be graded. It is going to be out of 5 points in total. Everything will be weighted, so each category will be a total of 1 point. Some things to keep in mind on this rubric. Point 1 here says you can use Google Maps to get the lengths and the areas of the various shapes. It has to make up the entire object. So just because you meet your 5 triangle requirement doesn't mean you stop. You find the area of the entire shape. You need to show all of your area calculations, even if it's for a square, a rectangle, or a circle. I need to see where it's coming from. You can use any polygons for this. Again, remember though, you must use the at least 5 triangles that you're finding, using law of sines and law of cosines, and you have to use the SAS triangle area formula at a minimum of 5 times. Your presentation must explain and show all the math for all the shapes you're finding, not just the triangles. And somewhere in your presentation, make sure to convince me that you're correct and that I should trust your analysis. Why should I believe the number you're reporting? Good luck with your project, and let me know if you have any questions.